which is the first root I found. So I said I'm just gonna substitute the value of s with this, which is the first root. I'm basically gonna get -1 plus square root of 2i times -1 plus square root of 2i plus 1 plus the square root of 2i. So all those cancel out. So -1 plus 1, they cancel out, and I get a2 equal to -12, and I get -1 plus square root of 2i times 2 times the square root of 2i. So a2 is actually equal to -12 over -2 times square root of 2i plus 2 times the square root, well, no, I don't have the square root anymore, times 2 I squared. So since I squared is actually equal to -1, I get a2 equal to -12 over -2 times square root of 2i plus 2 times 2 times -1 because of the I square. There we go. So a2, will we ever find a2? Yeah, we will. So bear with me. -12, can I write it 12? Okay, so over -2 times square root of 2i minus 2 times 2. So a2 is actually -12 over -2 times the square root of 2i minus 4. And then I can just rationalize by multiplicating for the complex conjugate of this one at the numerator and denominator in order to get rid of it. So a2 still -12. I'm just gonna rearrange and bring the -1 in front of everything because it looks more familiar. Generally, the imaginary number are at the very bottom, and the real number are at the very top. So -4 minus 2 times the square root of 2i, I just rearranged it, and then I'm going to multiply for the complex conjugate. So -4 plus 2 times the square root of 2i, or 2, sorry, I, which is outside the square root, -4 plus 2 times the square root of 2i. So a2 is actually going to be, well, -12 that multiplies all this. So -4 plus 2 times square root of 2i over 4 squared plus 2 times square root of 2 squared. This is what multiplying for the complex conjugate does. So a2 is actually, we're almost over, so 48, because negative and negative, 48 minus -24 times square root of 2i everything over 16 plus 4 times 2. So A2 is actually 48 minus 24 times square root of 2I over 16 plus 8. Okay, so A2 is 48 minus 24 times square root of 2I over 24, which finally gives us A2, which is 2 minus square root of 2I. Okay, so we have found A2, and I know what you're thinking. We have found A1, and then it took a hell lot of time to find A2. Do you have to do all this again for A3? Well, you kinda can if you want to, but I suggest you not to do it unless you want to check. If you want to double check it, feel free, do it. Test yourself with imaginary number, that's fine. But I'm just gonna tell you that every time you get those two complex roots, and you gotta find the poles are always gonna be conjugate between each other. So we can just easily say, okay, so therefore A3 is just 2 plus square root of 2I, because it's the conjugate of this one. Okay, so as I said, you don't have to find A3 from scratch again. So my I of s is, well, my I of s therefore is going to be I of s equal to 4 over s minus 4 over s plus 2 minus square root of 2I over s plus 1 minus square root of 2I plus 2 plus square root of 2I over s plus 1 plus square root of 2I, which gives me I of s, which is 2 minus square root of 2I over s plus 1 minus square root of 2I plus 2 plus square root of 2I over s plus 1 plus square root of 2I. So now I can finally apply the anti-transform of Laplace. So I of L, which is what it was asked, I of L of S, is just the anti-transform of Laplace of this whole thing here, so of I of S. So I just the anti-transform of Laplace of 2 minus negative 2I over s plus 1 minus square root of 2I plus 2 plus square root of 2I over s plus 1 plus square root of 2I. So I of L of s is just, well, we have found those square roots. So we're just gonna be, as always, e raised to the power of, and then we're gonna have the cosine and the arctan because of the way they are complex conjugate. So I of L is gonna be 2 times square root of 6 e to the negative t times the cosine of square root of 2t plus tan to the negative 1, so the arctangent of 1 over square root of 2. But it's not over. I know what you're thinking, but it's not over, because remember what we said at the very beginning. At the very beginning, we said that it's where was it? In the circuit is which, yeah. Then it goes back to position 1 after 1 second. So after 1 second, it's gonna switch to the previous one and it's basically gonna go back to position 1. So it's not over, guys. It's just not over. Because after 1 second, we will basically go back to position 1. So we will have this LR circuit, which I'm not going to solve with Laplace once again, because we can get a differential equation which is fairly easy to solve. But for the sake of getting my video right, we will have di dt equal to negative L over R EQ, the equivalent, times I, because it's an LR circuit, where R equivalent is actually 3 parallel to 1/2. So the R equivalent is just 3 over 2 divided by 7 over 2. So R equivalent is 3 over 2 times 2 over 7, just 2 cancel out, and I get an R EQ equal to 3 over 7. So di dt is actually negative 1 over 3 divided by 3 over 7 I. So di dt is negative 1 over 3 times 7 over 3 I. So di dt is negative 7 over 9 I. So let's solve it. Negative 1 over tau I, where tau is just negative 7 over 9. I of t is k, which is a constant in this case, e to the negative g over tau. So if we do the limit for t approaching positive infinite of IL of t, we get 4a. So I of L1 is IL of 1. So I of t is I of L of 1 minus I of L infinity, positive infinities, times e to the negative 1 over tau t plus 1 over tau plus IL infinity. So I of 1 instead is basically IL of 1 minus I of L infinity e to the power of 0 plus IL infinity, which just gives us IL of 1. So the limit for t approaching positive infinity of IL of t is just IL of infinity. But I just skipped this part. I just went straight to the end of this part, because the important one, the one that I wanted to show, this was just for the sake of solving the problem, right? But the real thing, the big deal, the real deal I wanted to show you was this first part here. So how to get to I of L using the Laplace transform. Here I didn't use it. I just went for the differential equation and so on, but it's not important. Here I just wanted to show you how to use the Laplace transform and how things work when you get two complex numbers as roots instead of real numbers.